All right, welcome everybody to the fifth Compass lecture of the semester. I want to introduce today's speaker, Caroline Hasler. She studied physics at ETH Zurich in Switzerland and graduated in 2022. For her graduate studies, she switched from physics to geology and is currently a second-year PhD student in earth and planetary science. Aside from hitting rocks with a really big hammer, she enjoys hiking, books, and browsing Berkeley's music stores. So let's welcome our speaker, Caroline.
Yeah, thank you for the introduction. So I'm Caroline. I'm really excited to be here today and talk to you about geochronology, which is the study of using rocks as clocks to investigate Earth's history. I'd like to start with a little bit of an introduction and kind of a motivation as to why this is important and why it's relevant also to you guys. Except I can't advance the slides. Sorry. Just do it like this. Okay. So you may at some point in your life have been to a museum. For instance, the UC Museum of Paleontology is right here on campus. And you may have seen some kind of sign or little plaque saying that the fossils and other objects you see in these museums are, for instance, 66 million years old. And you may have wondered, how do we actually know that age? It's not like paleontologists dug up this T-Rex from the ground with that handy-dandy sign attached. And you may never have asked yourself this question, but that's okay, because we're going to talk about it right here and right now. One of the ages that's really important for how we understand Earth's history and our own place on Earth and in the universe is the age of the Earth, which is 4.567 billion years. And if you ever want to impress someone at a party, this is a really easy age to remember because you literally just count 4, 5, 6, 7. So 4.567 billion years. This is a really long time, right? So to us humans, like 1,000 years seems like a really long time, but this is 4.5 million times older than that. So these are huge time scales. This age was properly measured for the first time in 1956, which is actually not that long ago. So to put this into perspective, when the age of the Earth was measured, our president was already a teenager. So this is not that long ago on geological time scales. And before that, for a long time, there was a lot of uncertainty about the age of the Earth. So previous estimate for the age of the Earth came from the Bible, which suggests that Earth is less than 6,000 years old. And obviously, there's a really big gap between these two numbers, right? 6,000 years is really lowballing the age of the Earth. So how did we get from this initial not very accurate 6,000 year estimate to the actual age of 4.567 billion years? Well, a lot of stuff happened in between, and in particular in the 19th and 20th centuries, geologists started to wonder about this estimate of 6,000 years, and it was pretty clear to them this would not be quite right. One of the reasons they realized that this couldn't be right was that they were looking at sedimentary rocks that we find on Earth. So this picture that I've put up here is a picture of the Grand Canyon. Some of you might have been to the Grand Canyon, and you may have noticed two main things about it. The first, it has these really deep canyons, right? Like really steep, tall cliffs. And the second, which you can see in this picture, is that the rocks have kind of a striped appearance, right? So they're built up of these individual layers, which are very fine. The individual layers that build up sedimentary rocks like this accumulate at a rate of about 1 millimeter per year or less. So a millimeter, for those of you who aren't familiar with the metric system, is really small. It's like 4% of an inch. And yet the Grand Canyon is like 5,000 feet deep, so about 1.5 kilometers, over 1.5 million times that rate of accumulation that happens in 1 year. So geologists, from looking at these kinds of rocks, they concluded that something like the Grand Canyon and other sedimentary rocks that we find elsewhere on Earth that are similar to this could not possibly have formed in the time span of 6,000 years. These kinds of environments must be at least millions of years old and possibly much, much older. So again, this was pretty clear to people who were actually looking at rocks and thinking about how they could have formed. But the question for a long time was, how do you prove that? How do you get hard evidence, unassailable evidence that Earth is much, much older than 6,000 years? The answer to this question, the missing piece, is radioactivity. Radioactivity was discovered in 1896, and it tells us that there are two main types of atoms. There are stable atoms that will form, and then they'll basically just sit around for a really long time. They might chemically react with other substances, but on their own, they're not just going to change their nature. They're not going to change their elemental type or their nuclear structure. But then there are also unstable atoms, and unstable atoms will undergo what we call radioactive decay, which means they will fall apart. And in this case, we call the radioactive atom, the unstable one, the parent, and the product of that radioactive decay is called the daughter atom. So kind of an analogy to the way human families and generations work. This process is called radioactive decay. I've included a diagram of a radioactive decay here. So we have a radioactive nucleus, which is, in this case, uranium-238. Uranium is probably one of the most famous radioactive substances, right? So if you saw Oppenheimer this summer, you'll know that we use uranium to make bombs. We also use it to power nuclear power plants as a source of energy. So this is a very radioactive substance, and it will decay by spitting out the smaller particle called an alpha particle to become a daughter, in this case, thorium-234. So this is one example I've named of a radioactive decay. Uranium will decay to thorium, and then eventually, through a series of other decays, it will decay to lead-206, which is stable. We also have a bunch of other decays. So for instance, potassium-40 will decay to argon, rubidium will decay to strontium, and there are a lot of other radioactive elements in nature that will undergo this kind of decay. The crucial fact that allows us to link this observation of radioactive decay to timescales in Earth history is that each radioactive decay has a characteristic timescale associated with it. This half-life, which I've denoted here as T1/2. This half-life is the time it takes for 50% of the parent atoms to decay into daughter atoms. So looking at an example, if we start at time 0 with 8 of these pink radioactive parent atoms, and we let them sit around for a while and just wait, they will decay over time. If we wait for exactly one half-life, half of those original parent atoms will have decayed into daughter atoms, so we'll end up with 4 parent atoms and 4 daughter atoms. If we wait a little longer, if we wait for another half-life, so we've waited a total amount of time of 2 half-lives, then once again, half of the atoms we had in this step, this first step after 1 half-life, will again have decayed into daughter atoms. So we'll end up with 2 parent atoms remaining and 6 daughter atoms. And the principle here is that we can see the number of parent atoms and the number of daughter atoms evolving over time in a predictable way, according to this characteristic half-life. We can use these radioactive decays as a clock to tell time. So to continue this example that I've used previously, I've just translated it into an analogy with an hourglass. If we start out with an initial amount of 8 radioactive parent atoms, so in this case, these pink grains that are in the top of the hourglass, and we just let that hourglass sit there, we totally forget about it, and we come back after a while and observe that we have 4 parent atoms left in the top half of the hourglass, and the other 4, so 50% of the original amount, have decayed and have now turned into daughter atoms at the bottom of this hourglass. Now, assuming I don't know how much time has passed, assuming I just left the room, forgot about this hourglass, came back and found it in this state. But if I know that it takes 4.5 billion years for half of the sand in general to flow down from the top of this hourglass to the bottom. How much time has passed since I left the room and left the hourglass in this original state? I see someone mouthing it. Do you have a guess? Yeah, it's 4.5 billion years, right? That was not a trick question, exactly. So one half-life has passed. We have half of the parent atoms left, half of them have turned into daughters. So again, without actually measuring the time in between, just by looking at the system and comparing it to its original state, I can get an estimate of how much time has passed. And that is exactly how we use these radioactive decays as clocks in research. So the age of the Earth, these 4.567 billion years, were measured in 1956 using the radioactive decay of uranium to lead. Uranium-238, like in our example with the hourglass we just looked at, has a half-life of about 4.5 billion years. So we can use this uranium decay to lead as a clock. We can also use all these other systems I mentioned earlier to tell us the ages of things like rocks, dinosaur fossils, other fossils, and basically any other object that you can dig up out of the ground that has some kind of radioactive material in it. The study of using radioactive decays to find out a rock's age or a sample's age is called geochronology, from the Greek word geo for earth and chronos meaning time. So we're looking at timescales and the timing of processes in Earth's history. And that's what I do in my research. So specifically, I use geochronology to study major magmatic events in Earth's history. Right now, I'm looking at widespread magmatic stuff that happened in Europe at the Carboniferous Permian boundary, which is a fancy geological way of saying about 300 million years ago. I'm interested in this period because we don't really know what caused this really widespread volcanic and magmatic activity. So I'm hoping to get some clues about that by looking at the timing of these processes. And we also don't really know how this could have affected Earth's climate. When you think of really big volcanic eruptions that happen on Earth today, they tend to have some kind of observable, measurable impact on Earth's climate. So the question is, can we, by looking at these events, try to reconstruct possible climate effects of that volcanic activity? The way I do this is by measuring uranium lead amounts in these microscopically tiny crystals called zircons. And I'd like to spend a little bit of time talking about zircons because they're very cool crystals. So this is a picture of a zircon that was actually taken under a microscope. Again, these are very small, so you can't see them like this with your naked eye. But this is what they look like. They have this typical kind of stereotypical Disney crystal shape. They're smaller than a grain of salt, in case that's a useful size reference for you. They consist of zirconium, silica, and oxygen, and they crystallize out of magma, so molten rock, in Earth's interior. The recipe for how to make a zircon is you melt rock in the mantle to produce a magma. That magma will rise up towards Earth's crust and collect there in these big magma chambers. The magma chambers are where the zircons crystallize out of the magma. So as the magma cools, individual minerals will start to solidify, and zircons are some of those minerals. That magma will then be erupted as lava from volcanoes, and the zircons will be erupted with it onto Earth's surface, where we can collect them and date them today. The special thing about zircons is that most rocks and minerals only last 1 to 100 million years. And I've put this in quotation marks because obviously this sounds like a really long time to us. But when you think about the timescales of processes in Earth's history, again, 4.567 billion years is the age of the Earth. This is actually not that long, right? So most rocks, for example, have not survived since the beginning of Earth's history. In fact, we have no rock record, no solid piece of rock from the initial phases of Earth's history. And this is because various processes on Earth conspire to destroy rocks and minerals. So chemical dissolution can happen, weathering by rain, other processes like subduction and tectonic forces that crush and destroy these rocks with huge pressures. And they can all destroy rocks and minerals. But zircons are extremely resilient, and they can really survive almost anything. So the oldest zircons we have are actually about 4.4 billion years old, meaning these zircons have been around for most of Earth's history. And this is pretty amazing when you think about what Earth looked like at the time. This is an artistic reconstruction of what Earth's early history looked like. So people think that at the time, Earth was in kind of a magma ocean state. So most of the surface was molten. There was no solid rock. There were no mountains. There was no Berkeley or San Francisco. And there were meteorite impacts happening all the time as well. And the first zircons actually crystallized out of this magma really early in Earth's history. And they've survived since then for 4.4 billion years up until today. So zircons really do record an incredible amount of Earth history. And by studying them, we can get a lot of information about what Earth looked like at a time when we have no other information, when we have no fossils even, because there was no life yet on Earth. So we can use zircons as rock clocks because fresh zircons, when they're produced out of a magma, they contain uranium. Again, this uranium is unstable and will decay to lead. And then we just measure the relative amount of the parent, uranium, to the daughter, lead, like we did in our example before, to figure out the age of the zircon. And we can use them to study ancient volcanic and magmatic events today, millions or billions of years after the actual events happened. Okay, so that's kind of the basic principle of what I do in my research. And I'm happy to answer questions about that a little bit later, but for now I thought I'd spend some time talking about what I actually do in my day-to-day life as a researcher. So how do we get from a rock to this data to an age for something that we can write on a sign in a museum? Well, the first step is to actually go out into the field and collect a bunch of rocks. So that's what I did this summer. I did fieldwork in Germany and Sweden. Here I am sitting in a quarry in Sweden. That's where I am in case you missed me, collecting some rocks. You can see I'm kneeling next to this huge mass of chunky black stuff. That chunky black stuff is a bunch of magma that came up through Earth's crust about 300 million years ago and cooled and solidified there. And in this picture, I have just finished smashing a bunch of that rock out of the cliff face with a really big hammer and putting it in a bag to take home for further study. Here are some more pictures of my fieldwork in Sweden. This one on the left here was my view for lunch one day. This is probably one of the most beautiful places I've ever been to, and I still can't quite believe that someone actually paid for me to go there and collect a bunch of cool rocks, which is pretty much a dream come true. Here in this picture, you can see me again bagging a sample and taking some notes in the field. All this chunky gray stuff that I'm sitting on is, again, part of a magmatic complex that is about 300 million years old and that I'm sampling for geochronology. This rubble field on the right is another area where I looked for samples, and I put it in here to kind of show that it's not always easy to see what you actually want to sample. So here on the left, it's pretty clear that this chunky stuff is all the same material, and it was pretty clear that that's what I was looking for. Here on the right, if you just have a bunch of really messed up looking rocks, it's a lot harder to see. So that's one of the challenging but also really interesting parts of fieldwork, is that you always have to kind of use your Sherlock Holmes detective brain to figure out what happened to Earth's surface. Step 2 is crushing the samples. So this is a picture of me holding a really big hammer, standing next to one of my victims, soon-to-be victims, a rock sample. This is very therapeutic, by the way. If you ever get the chance to smash a rock in real life, it's a lot of fun. I would definitely recommend it if you have any frustration you need to vent. Just to add a little disclaimer, when you're actually crushing a rock, if you ever do get that opportunity, please wear eye, nose, and mouth protection, because pieces of rock do fly all over the place and it's very dangerous. So I usually also do wear eye, nose, and mouth protection. I'm just not wearing it for the picture. But again, very fun, would recommend. Then there are a couple of kind of boring steps, and the next really important one is actually picking out the zircons, these tiny crystals that are going to make up the sample that we want to measure. I was telling this to a friend of mine, and she asked, wait, how do you pick the zircons? Do you just use really tiny tweezers? And the answer is yes, we use really tiny tweezers to pick out these zircons under a microscope. So here on the right, we have an image of a sample preparation room at the Berkeley Geochronology Center, where I do most of my research. And you can see we have a bunch of microscopes lined up, samples in various stages of preparation. So at this point, we're really just taking a dish full of crushed up rock and picking out the zircons that we want to use for our sample. Okay. Here for this next step, this is kind of a bittersweet step. So these zircons have survived a lot of stuff, right? And in particular, the ones I'm looking at have survived 300 million years of geological stuff that's happening to them. So that includes volcanic eruptions, a bunch of plate tectonics, all the weird weather at Earth's surface. But to date, these zircons, to get the information that they contain, we actually need to dissolve them. So sadly, although these zircons have survived so much in their lifetime, we have to come up and say, okay, that's cool, thank you, but your time is up. What we do is we hit them with really strong acids to dissolve them. Again, these zircons are incredibly resilient, they're very stable, so the only way to dissolve them is to use some of the really strong acids that we know, hydrofluoric acid in this case. Here's just a picture of a tub of hydrofluoric acid. So hydrofluoric acid will dissolve a lot of stuff. It will dissolve most metals, it will dissolve things like bricks and glass, and also your bones. So if you get some of this on you, it can actually like leach down through your skin and through your flesh and dissolve your bones inside your body. I know it's Friday, October 13th, we have Halloween coming up. This is pretty spooky stuff, right? If you had any skeletons you wanted to get rid of, you could just dissolve them with hydrofluoric acid, as long as you make sure it's not your own skeleton. So you want to be careful when you're working with this stuff, right? A lot of this work is done in a clean lab. And when I say clean, I don't mean the kind of clean where your mom is coming to visit, so you like run a Swiffer over the dusty surfaces in your apartment. I mean clean as in we're trying to avoid contaminating our sample with any amount of lead or uranium. So like even individual atoms of lead can be a problem here. And this is pretty tricky because you might not think of lead as something that you interact with a lot in daily life. But in fact, most metal objects will contain little amounts of lead. So if you're wearing metallic jewelry, that can be an issue. Also, certain beauty products, certain shampoos, perfumes can contain traces of lead. So again, this can be very tricky to deal with when you're in the lab. We have this kind of setup in the clean lab. Again, this is a microscope. You can see that here all of the stuff under this on this desk is made of, it is like in these containers that are sealed. We also have this grating in the back. This table is actually standing under a fume hood that sucks all the air away from you and up, so that even if you're leaning over a sample or working on it, anything that like falls off of your hair, if you have blood in your hair or on your glasses or something, it will end up in the sample and won't contaminate that sample. So this is very tricky. You have to be very careful. It's a very clean kind of work environment. And again, this is a picture of the entrance to our lab. You can see there's a caution sign for radioactive materials. So it's a VIP area, authorized personnel only. This is because we are in principle working with uranium, right? But again, we're working with the uranium that's naturally present in the zircons. So if you've ever gone outside and ever picked up a rock, that's the kind of uranium level that we're dealing with, right? So we're not quite at the level where we're building bombs or anything. Then step 5 is actually measuring the amounts of uranium and lead that are present in the sample. And to do that, we use a mass spectrometer. Here's the one that I use at the Berkeley Geochronology Center. So what you do is you put the sample in this thing here and it vaporizes your dissolved bit of zircon and shoots it through that tube that you can see up there and counts the amount of uranium and lead atoms in the sample. And then the last step is using that information to get the age from the sample. Okay, so that's basically not just a day in the life, but more like a couple of months in the life of this process of geology and geochronology. To end, I wanted to talk a little bit about how I got here. So I sometimes describe myself as an accidental geologist, or if there are no physicists in the room, I might get bold and say I'm a recovering physicist. So my bachelor's degree is actually in physics, as was mentioned earlier. I got my degree from ETH Zurich in Switzerland in 2022. Over the course of my undergraduate degree, I did some undergraduate research, and it was mostly actually in the field of astronomy and planetary science. So I did a project looking at the orbits of exoplanets, planets that orbit other stars than our sun. I also did some numerical modeling of planetary interiors, looking at the convection in the inside of planets. And I did enjoy the research. I liked my physics classes, but especially towards the end of my degree, I could tell that something was missing. And in particular, I realized towards the end of my degree that while I enjoyed learning about physics, I didn't want to actually be a physicist. I couldn't imagine actually doing any of the jobs that you think of physicists doing. And this was a little bit of an issue because I was beginning my senior year of college, which is the time when you're supposed to start thinking about applying to graduate school and figuring out what you want to do with your life. And so I knew that I had limited time to figure out what I actually wanted to do with my soon-to-be completed physics degree. I knew that I liked earth science, so that was an idea that I had for a direction I could go in. I grew up in Switzerland, so I spent a lot of time in the mountains and hiking. I was also one of those kids who likes to collect rocks, to the great chagrin of my parents, who always had to deal with me dragging home bags of rocks after every vacation. And I was taking earth science classes as well during my undergrad, but I was kind of struggling to figure out how I could combine my interest in earth science with my interest in physics. And the epiphany for that came while I was sitting in a class one day, a class taught by Professor Susan Ivy Ox, who was a geologist and geomorphologist at my alma mater, ETH Zurich. And she was talking about her research, which uses a kind of sub-technique of geochronology called cosmogenic isotope geochronology. And I was sitting in class and I found myself thinking, oh, that's something I could actually imagine myself doing. So I waited until class was over and I approached her and introduced myself and asked her if I could do an undergraduate research project with her. She said yes, and I ended up doing an undergraduate research project, my last one, on cosmogenic isotope geochronology. And then I ended up here. So I wanted to end with some cheesy life lessons for any undergraduates who might be listening. I don't know what level you're at. You might be juniors or seniors, and you might be starting to feel the pressure of having to decide what you want to do with the rest of your life. And there are always some people who have known what they wanted to be and do since they were 4 years old. And that's great if you're one of those people. But I was not one of those people, and I think most people aren't. So I just wanted to say that it's okay to take your time figuring out your plans. You will end up doing something with your life, and it will probably be something really interesting. But you don't need to know that right now. You can take an extra year if you have to figure out whether you want to go to graduate school. You can take your time figuring out what kinds of jobs you might like to try. It's okay. In that time, don't be afraid to explore, to try out new things. Especially here at UC Berkeley, you have a really unique opportunity to get world-class guidance and educational opportunities in almost any field you could imagine. So take those chances, take those opportunities, and also be bold enough to ask for opportunities. It can be really hard to just walk up to a professor or a lecturer you don't know and ask for something. I think especially for those of us who did part of our undergrad during COVID, when we had basically no contact with professors, that's the case, that's the situation I was in, it can be really daunting to just approach someone and ask for help, for a favor, for a research opportunity. But I would definitely encourage you to do that, because if you don't, you're missing out on a lot of really cool experiences and maybe an epiphany about what you'd like to do with your life. And then finally, I wanted to point out that it often feels to people like, and it felt like to me, that your degree determines your future trajectory, right? If you have an engineering degree, you're going to be an engineer. If you have a physics degree, you're going to be a physicist. But I wanted to point out that actually your degree, your background, your grades, the classes you've taken, they really don't determine what you'll end up doing. They do not determine your future. The only power that can determine your future is you. So be proactive about it, explore, ask for opportunities, and you'll end up doing something really cool. Okay, that's all I had to say, and I'll be happy to answer any questions. Thank you.
Either in person or on Zoom.
Oh, okay. Thank you. Thank you for the applause.
I have a question.
Yeah.
I don't know if you've ever, you mentioned earlier in your talk that we don't have any rocks from like the Earth formation.
Yeah.
Do you know of any research or anything about other planets formation, and like are you able to like compare like what like Earth may have looked like by looking at maybe another planet that might be earlier in their
That's really interesting. So you mean planets in other solar systems, planets orbiting other stars? Yeah, that's an interesting question. So I don't know if we have enough information about those planets yet. Again, I'm not a planetary scientist and astronomer, but most of the planets that we've discovered so far, we have very limited information about them because we can't take enough high resolution images of them. We obviously can't get samples from them. But definitely something that's been done to try to illuminate the age of the Earth is looking at the moon, right, which is our closest neighbor, which has survived a lot of the same history in terms of just the asteroid impacts that have happened and that kind of stuff. But the moon, unlike Earth, does not have weather. It doesn't rain on the moon, and it also doesn't have plate tectonics. So the rocks that form on the moon, they just sit there and survive. And one of the things that was done after the Apollo missions, when we got samples back from the moon, was doing geochronology to figure out how old these rocks are. And there we do really have rocks that are 4 billion years old, which is way older than any of the rocks we find on Earth. But there is kind of a fun competition going on between some geologists here on Earth to try to find the oldest rocks and the oldest zircons. So that's definitely something that's happening as well, trying to push the limits of those techniques to see farther and farther back into Earth's history.
Any questions? I think I speak for one more time.
Thank you.